And welcome to GED Live at PALS with teacher Alex for another GED science lesson. Today's topic is atoms and bonding and the structure of matter. A quick overview. We will learn about the atom and the subatomic particles, the particles that atoms are made of, the atomic structure and what the atomic number and mass number is. We will learn what ions and isotopes are. We will learn about the octet rule and the stability of atoms, and about the different types of bonds, ionic, covalent, and metallic. The atom is the smallest unit of matter that has the characteristic properties of a chemical element, such as the atom is the basic building block of chemistry. It also is the smallest unit into which matter can be divided without the release of electrically charged particles, a bit more advanced definition. Most importantly to understand is the first sentence, that it's the smallest unit of matter that has the characteristic properties of a chemical element. So it's the smallest part you can have of an element. One particle of an element is an atom. You cannot have less of that. We can break the atom down, but then we will have different elements and not that particular element anymore. We see a depiction of the atom here. You can already see we have the different particles, which we will discuss in a minute. We have a nucleus in the center of the atom, and then we have electron shells around that nucleus. So what is an atom made of? We already saw in the figure before that the atom consists of protons, neutrons, and electrons, which are part of the smaller fundamental particles, combinations of these, and these are the three that we will have a closer look at. So the proton has the symbol P+. It has an approximate relative mass of 1 and a relative charge of 1+, and it's found inside the nucleus. The neutron has the symbol N, a mass of 1 as well. It has no charge. It is neutral in charge. That's where the name comes from. A neutron is neutral, and it's found inside the nucleus as well. Electrons, the symbol E-, have basically no mass compared to the protons and neutrons, so we can neglect that small number and say it's 0, and the relative charge is 1-. It is not found inside the nucleus, but in distinct regions, the electron shells around the nucleus. The relative mass of 1 doesn't have a unit. It's not 1 gram or something, or milligram. It's on a scale where that is based on 1/12 of the mass of a carbon-12 atom, and that is equivalent to 1 atomic mass unit. So a carbon atom has a relative mass of 12, a proton based on that relative mass, a mass of 1. Okay, element symbols or isotope symbols. We have a mass number A, which is the sum of protons and neutrons in the atom. As we saw before, the particles that have mass are protons and neutrons, so the mass number is the sum of the number of protons and neutrons in the atom. It's as well called the nucleon number because protons and neutrons are the particles of the nucleus. Z is the atomic number, and that is the number of protons. The number of protons defines our element. If your atom has 1 proton, it's a hydrogen atom. If it has 2 protons, it's a helium atom. If it has 3 protons, it's a lithium atom, and so on. Sometimes we see a charge that is due to an imbalance of protons and electrons. We will talk about that later in detail. But usually if we have an atom of an element, the number of electrons is the same as the number of protons, and the charge is balanced. In an atom we don't have an overall charge. The overall charge is 0 because the number of protons and electrons are the same. If we want to find the number of neutrons in an atom, we subtract the atomic number from the mass number. Since the mass number is the sum of protons and neutrons and the atomic number is the number of protons, that's how we find the number of neutrons. So, what are isotopes? Isotopes of an element are atoms of the same element, which means they have the same number of protons, but they have different numbers of neutrons and hence different mass. Examples of the isotopes of carbon are shown below. We have carbon-12, carbon-13 and carbon-14. These are the three isotopes of carbon. Carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons, and carbon-14 has 6 protons and 8 neutrons. We see a percentage. This percentage tells us about the abundance of these elements. 98.9% of all carbon atoms on Earth are of the carbon-12 isotope. 1.1% are of the carbon-13 isotope, and there's only a trace of carbon-14 isotopes, which is smaller than 0.1%. The element symbol that we find in the periodic table is a little bit different from the isotope symbol that we saw before. We can see that instead of the mass number, we have the relative atomic mass, which is a decimal number, 12.011. We cannot have partial neutron. We cannot have 0.1 neutrons or protons. So how do we get to this decimal number? The atomic mass is a decimal. It represents the weighted average of the relative atomic masses of the isotopes of carbon. The weighted average takes the abundance, or the percent abundance, of the isotopes into account. So it's like calculating the average mass of the carbon-12, 13 and 14 isotope, but taking into account that 98% or almost 99% of all carbon atoms are of the carbon-12 isotope. Calculating the average, we get to the relative atomic mass of 12.011. What are ions? As we already said earlier, atoms of an element have the same number of protons and electrons, and hence are of neutral charge. The atom has a net charge of 0. An ion is an atom with an electrical charge due to a different number of electrons than protons. A positive ion, so-called cation, has less electrons than protons. It has lost electrons. And cations are usually formed by metals, because metals tend to lose electrons to form cations. Why that is, we will learn later on. A negative ion, an anion, has more electrons than protons. Non-metal atoms usually gain electrons and form anions. The amount of charge is then displayed in the right corner. If it's 2 positive charges, it's written as 2 plus. If it's 2 negative charges, 2 minus. 3 negative would be 3 minus, not minus 3 or plus 2. First the number, then the sign. So again, how do we get to a cation or an anion? If electrons are gained, it becomes negative. If electrons are lost, it becomes positive. And that's a bit counterintuitive. Usually with gain we associate positive, with loss we associate negative. However, keep in mind that what is lost and gained are electrons, and electrons are negative. So if we gain something that is negative, it becomes negative. If we lose something that's negative, we become positive. So here we have an example of an ion formation. we have a neutral atom, in this case a calcium atom, with 20 protons and 20 electrons. That calcium atom will lose 2 electrons and it becomes a calcium ion, a Ca2+ ion, with still 20 protons and now only 18 electrons. Again, the proton number stays the same. If the proton number should change, then it wouldn't be calcium anymore. Every atom with 20 protons is calcium. So a quick summary: when the number of electrons change, an ion forms. When the number of protons changes, which happens in nuclear decay and radioactive atoms, the element itself changes. When the number of neutrons changes, the masses of the atoms will be different, and these atoms with different masses are called isotopes. So why do atoms lose or gain electrons, and why do ions form? This brings us to the octet rule and the bonding. The octet rule states that atoms are in a more stable state when they have 8 valence electrons, or 8 electrons on the outer shell. Valence electrons are the outer shell electrons. This is as well called the noble gas configuration, since all noble gases from group 8 in the periodic table, far on the right side, naturally have 8 valence electrons. All other elements have to get to the stable state by either gaining, losing, or sharing electrons. In the process of doing this, chemical bonds and compounds are formed. The types of chemical bonds we will discuss now. There are ionic bonds, covalent bonds, and metallic bonds. Below here we can see an example of potassium atom. It has 4 shells. The outer shell is the 4th shell. And we can see that the potassium atom itself is not stable because it has 1 electron on its outer shell. The easiest way for potassium to become stable is losing that 1 electron, and then the 3rd shell becomes the outer shell. And the 3rd shell already has 8 electrons. So the atom will then be stable. Since we learned previously that metals are the ones that lose electrons and form positive ions, we can conclude that potassium must be a metal. Let's move on to ionic bonds. Ionic bonds form between metals and nonmetals. Metals lose electrons to gain a full outer shell and form positive ions. Nonmetals gain electrons to get a full outer shell and form negative ions. That usually happens at the same time when metals bond with nonmetals or react with nonmetals. Metals will lose the electrons and the nonmetals will gain the electrons lost. Metal and nonmetal ions bond together because of electrostatic attraction of opposite charges. Since metal ions are positive, nonmetal ions negative, they attract, and an ionic compound forms. The charge of the ionic compound is always neutral, thus the charges of the ions must balance. Remember that the reason why the ions form in the first place is to have 8 valence electrons. So every ion always must have 8 valence electrons. 8 electrons on the outer shell. So here an example. If sodium reacts with chlorine, sodium has 1 electron on its outer shell, whereas chlorine has 7 electrons on its outer shell. The easiest way for sodium to get to 8 is losing an electron, whereas the easiest way for chlorine to get the full outer shell is gaining an electron. So here we have a perfect match. Sodium loses 1 and chlorine gains 1. We will get a sodium ion which has 1 positive charge, 1 plus we just write as plus, and a chloride ion forms, which is Cl minus. The negative ions usually have different names compared to their elements, so we can see here we have the element chlorine and its negative ion chloride, whereas the metal ions usually have the same name as the elements. We have the sodium atom and the sodium ion. Since opposite charges attract, a compound forms, and that compound is called sodium chloride. Another example is, for example, magnesium reacting with fluorine. In this case, fluorine atoms have 7 electrons on their outer shell, but magnesium 2. So magnesium needs to lose these 2 to get to a full outer shell. However, a single fluorine atom is now not enough because fluorine only wants to gain 1 electron. So magnesium loses its 2 electrons and 1 will go to each of the 2 fluorine atoms. The resulting compound consists of a fixed ratio of 1 magnesium 2 plus ion and 2 fluoride 1 minus ions. The net charge of the compound again will be 0 because 2 positive charges from the magnesium ion and the 2 negative charges of the combined fluoride ions will cancel each other out. The resulting formula of magnesium fluoride will be MgF2. Covalent bonds. The second type of bond formed between non-metal atoms. To gain a full outer shell, atoms share electrons. One covalent bond consists of a pair of shared electrons where each participating atom contributes 1 electron to the bond. The number of covalent bonds an atom forms is equal to the number of electrons it needs to gain to get to a full outer shell. There are 3 types of covalent bonds that can form between atoms. We have single bonds, which involve 1 shared electron pair, double bonds, 2 shared electron pairs, and triple bonds, 3 shared electron pairs. Some examples of covalent bonds forming. We can see we have hydrogen forming a hydrogen molecule, H2. We can see chlorine forming Cl2. We can see methane forming CH4 and water forming H2O. One thing I did not mention earlier in the octet rule is that it has an exception. The exception is that when the first shell is the outer shell, it is stable with 2 electrons. Since hydrogen has only 1 shell, the first shell, it will be stable with 2 electrons. The electrons in the covalent bond count for both atoms. So we can see on top that hydrogen, once bonded, has 2 electrons, each of them. They count for both species. We can see carbon having its own 4 electrons plus the 4 from the hydrogens, making it 8 as well. We can see oxygen bonding with hydrogen, making 8 electrons as well. Again, 2 for the hydrogens, which is stable for the hydrogen. And the 2 chlorine atoms will have each 8 electrons on their outer shell, 2 by sharing. Some more examples of covalent bonds. We can see them here now in more detail and the different possible representations. An example as well where we have a double bond is CO2, where we have the double bonds here. Each single line represents 1 shared pair of electrons. Metallic bonds. Metallic bonds form between metal atoms. Metals form giant structures in which electrons in the outer shells of the metal atoms are free to move. The metallic bond is the force of attraction between these free-moving, so-called delocalized electrons and the positive metal ions. So the outer shell electrons are basically expelled by the metal atoms. They form positive ions with a full outer shell, and the expelled outer shell electrons can now move freely around between the positive metal ions. They stick around due to the attraction, and the attraction between the delocalized electrons and the metal ions are the metallic bond, which is a really strong bond. As we know, most metals are strong solids at room temperature. Another depiction of that we can see on the right here, the lattice of positive metal ions and around them the free movable electrons. Since the electrons can move around freely between the metal ions, this is the reason why metals are good conductors of electricity. By applying positive and negative charge on both sides of a metal, we give these electrons a directed flow from negative to positive pole, and an electric current is flowing. In non-metal substances where we have covalent bonds, all electrons are occupied, and these are not good conductors of electricity, since there are no free movable electrons. So, summary, we have the ionic bond of oppositely charged ions arranging themselves into a lattice, covalent bonds of shared electrons, and metallic structures with delocalized electrons and their possible paths around the positive metal ions. Some questions at the end. How many protons does the carbon atom have inside its nucleus? As you can see, you can pause the video if you want to think about the answer. The answer is coming now. The correct answer here is B, 6. The atomic number is 6, the mass number is 12. The proton number is equal to the atomic number, so the answer is 6. Another question, the table shows information about 4 different particles. What are the values of W, X, Y, and Z? W is here, X is here, Y is here, and Z is here. The information that we get about these particles, sodium ion, Na+, oxygen atom, and the oxide ion, O2-, are the proton number, mass number, number of protons, number of neutrons, and number of electrons. Some are missing. You can stop the video now and think about the correct answer. In this case, the correct answer, let's figure it out together. Sodium has the mass number 23 and the proton number 11. To find the number of neutrons, we take the mass number minus the proton number. 23 minus 11 is 12. So W must be 12. So it's either C or D. How many electrons does Na+ have? We have 11 protons. The overall charge is positive. That means we have 1 less electrons than protons. So we need 10 electrons. That will give us 1 positive charge. Again, if you remember, protons are positive, electrons are negative. 11 plus and 10 minus will give 1 plus. How many neutrons does oxygen have? It has a mass number of 16 and a proton number of 8. To find the neutrons, we take the mass number minus the proton number, so the Y will be 8. How many electrons does O2- have? We have 8 protons. 2 negative charge means we need 2 more electrons than protons, 10 electrons. So the correct answer here is C, 12, 10, 8, 10. Alright, that's it from me, Teacher Alex, here with GED Live at Phuket PALS. This was a screencast on the structure of matter, atoms, and atomic bonding. I hope to see you next time.